Hello and welcome back. Today we will look at sequential continuity. Remember, here's the setting. We have a function that goes from a metric space M, um, which has its own distance function, to another metric space N. And then let P be a point in M. In last video, we defined what it means for this function f to be continuous at this point P in M. And now we are going to define what it means for this function to be sequentially continuous. And we are just using the term sequentially continuous because it's a new definition and we don't know yet that it's going to be equivalent to the definition of continuity, so that there's no need to distinguish between these two definitions. But that's a spoilers for you. Sorry about that. But let's just look at sequential continuity. Let's think of it as its own new definition, and on the next video we will see, or we will try to prove why it's the same thing as continuity. Here's the setting. Let me give you an example. Suppose we have a real number r with distance function given by the absolute value, where distance between 2 points x and y is the absolute value of the difference between x and x minus y. So suppose we have something like this, the usual distance function in real line. And suppose you have a function f from r to r. And let's look at a function that's not continuous in our usual sense of analysis. And this is r, thus r. And suppose we have the absolute value function, f of x equals, let's look at the floor function. So this function looks like, that's 1, that's 2, that's 3. So it's down here between 0 and 1. And then once you hit 1, then it just goes up. It goes like this, and it goes like this. Now, so that's our function. Let's look at the point 1. So let P be point 1. So if we look at a sequence of function that goes towards 1, say for example, 1, what should we do? Let's do 1.1, 1.01, 1.001, 1.0001, and this function, and this sequence. If you look at this sequence, if our xn is this sequence, then what would f of xn be? So we know this sequence tends to 1. Now f of xn, if you look at the floor function, it'll just be 1, 1, 1, 1. And this will tend towards 1 as well. So in this case, and f of 1 equals 1, obviously. So in this case, what we have is that xn tends to x, where x equals 1, and f of xn tends to f of x. Let's look at another example. If we let our sequence to be, say, 0.9, 0.99, 0.999, and so on, this thing tends to 1 as well. This sequence tends to 1 as well. But if we look at f of xn, and that will be, because of the floor function, be 0, 0, 0, 0, and that will tend towards 0. Now, here's the thing I want you to notice. In this case, although xn tends to 1, f of xn does not go to f of 1. Because f of 1, the floor function of 1, is equal to 1. However, f of xn, this sequence is a sequence of zeros, so it tends to 0. So, and the reason it happens is because we sort of see at this point 1, the function isn't continuous. So we'll define the sequential continuity. A function between metric space M with its own metric to n is called, let's say, is said to be sequentially continuous. Say at some point p in M if, so here's the situation. If for any sequence xn that tends to p, we have that f of xn tends to f of p. And our previous example was an example of a function that's not sequentially continuous at the point 1, because we had this sequence that did not satisfy the definition of sequential continuity. Okay, hope you enjoy this video, and on the next video we will try to prove why sequentially continuous means the same thing as being continuous. I will see you then.